I want to tell you something about your left hand, not about its bones or its tendons or the network of nerves that allows you to feel the pressure of this moment. I want to tell you about the atoms, the specific atoms, the carbon atoms in your skin, the calcium atoms in the bones beneath it, the iron atoms in the blood moving through the veins. You can see tracing blue lines across the back of it. I want to tell you where those atoms were before they were part of you, not in a vague poetic sense, in a precise, physical, historically traceable sense. Because each of those atoms has a biography that begins not on Earth, not in the solar system, not even in anything that existed when the universe was young. Each of those atoms was forged in the core of a star. And most of them arrived here because that star died violently in an explosion so powerful that for a few weeks it outshone the entire galaxy it lived in. You are made of stellar explosions. That is not a metaphor. It is nuclear physics. But I want to go further than the statement usually goes, because I think the way this idea is typically presented sells it short. We say you are made of stardust, and we treat it as a beautiful closing thought, a poetic flourish at the end of a science documentary. What I want to do today is take it apart. I want to trace the specific nuclear reactions that built the atoms in your body. I want to tell you what kind of star made them, how large it was, how long it lived, and what it felt like, insofar as physics can say anything about what a dying star feels like from the inside. I want to tell you about the specific candidates, the actual stars in our galactic neighborhood, whose deaths contributed the atoms that eventually became you. And I want to sit with what it means, genuinely means, not as sentiment, but as physics, that you are the most recent chapter in a story that began 4 billion years before the Earth existed. Let me start with the simplest atom, hydrogen. Most of the hydrogen in your body, the hydrogen in the water molecules that make up about 60% of you by mass, the hydrogen in the organic molecules that make up everything else, did not come from a star. It is older than stars. It is older than galaxies. Hydrogen is the element that the Big Bang produced directly in the first few minutes after the universe began, when temperatures were high enough for protons to fuse, but low enough for them to remain as individual nuclei rather than collapsing further. The hydrogen in your body is 13.8 billion years old. It has been a gas cloud, part of an interstellar medium, a component of nebulae, a constituent of ocean water, a molecule in the atmosphere, and now it is you. But it was never inside a star. It arrived directly from the first moments of the universe. The helium in your body, and there is very little of it because helium is chemically inert and does not form compounds, also came mostly from the Big Bang. Primordial nucleosynthesis, the process that occurred in the first 20 minutes of the universe's existence, produced roughly 75% hydrogen and 25% helium by mass, with trace amounts of lithium and beryllium. Everything else, every element heavier than helium, everything that is not hydrogen and not primordial helium, was made inside stars, or in the collisions between stars. This is the central fact I want you to hold. The periodic table is divided fundamentally into two regions. The region that the Big Bang made, hydrogen and helium, and the region that stars made, everything else. Carbon, nitrogen, oxygen, phosphorus, sulfur, the elements that build your DNA. Calcium, the element in your bones. Iron, the element in your blood. Iodine, in your thyroid. Zinc, in your enzymes. Copper, in the proteins that carry electrons in your cells. Every single one of these was assembled inside a star by nuclear reactions operating at temperatures and pressures that are completely impossible to replicate in any laboratory we have ever built, in any environment that exists naturally on Earth. So let me take you inside a star. A star is, at its heart, a fusion reactor. Not a fission reactor, the kind that splits heavy atoms to release energy, but a fusion reactor, the kind that merges light atoms into heavier ones. The energy that keeps a star from collapsing under its own gravity, the energy that makes it shine, comes from the conversion of mass to energy that happens every time lighter nuclei fuse into heavier ones. The heavier nucleus weighs slightly less than the sum of the nuclei that combine to form it. That missing mass becomes energy, according to Einstein's equation that most people know but few people fully appreciate in this context. E equals mc squared. The c squared term is enormous. A tiny amount of mass becomes a stupendous amount of energy. The fusion sequence in a star follows the periodic table in a rough order of increasing atomic weight, but the sequence is not smooth or continuous. It proceeds in stages, each stage requiring higher temperatures and higher pressures than the one before, each stage producing energy but less efficiently than the stage before, and each stage lasting for a shorter time than the stage before. A star's life, from the outside, looks like a single sustained event. From the inside, it is a series of distinct nuclear eras, each one shorter than the last, each one producing different elements, building the periodic table layer by layer in the star's interior. The first stage is hydrogen burning. Protons fusing to form helium nuclei. This is what a star spends most of its life doing. Our sun has been in this stage for about 4.6 billion years and will remain in it for roughly another 5 billion. The temperature required for hydrogen fusion is about 10 million degrees Celsius. The sun burns through roughly 600 million metric tons of hydrogen every second and has been doing so for longer than the Earth has existed. This stage produces helium and enormous amounts of energy, but no elements heavier than helium. When the hydrogen in the core is exhausted, the core contracts. Gravity is always pulling inward, and as long as fusion is occurring, the outward pressure of the energy produced holds the star up. When fusion stops, the core contracts. Contracting means compressing. Compressing means heating. The temperature in the core rises, and at about 100 million degrees Celsius, something new becomes possible. Helium nuclei begin to fuse. The fusion of helium is more complex than hydrogen fusion, and the product is remarkable. 3 helium nuclei can combine in a two-step process called the triple alpha process, named because helium nuclei are also called alpha particles, to produce a carbon nucleus. This is the reaction that built the carbon in your body. 3 helium nuclei, each with 2 protons and 2 neutrons, combining to form 1 carbon nucleus with 6 protons and 6 neutrons. Carbon, the element that is the structural backbone of all organic chemistry, the element that makes the variety of life possible, is produced by a nuclear reaction that requires 3 helium nuclei to collide almost simultaneously, which is a statistically improbable event that only becomes likely at the extreme temperatures and densities of a stellar. The fact that carbon is produced at all is actually one of the most startling coincidences in nuclear physics, and I want to spend a moment on it because I think it deserves more attention than it usually gets. The triple alpha process has to pass through an intermediate step, the fusion of 2 helium nuclei to form a beryllium-8 nucleus. Beryllium-8 is extraordinarily unstable. It has a half-life of about 10 to the minus 16 seconds. It decays almost instantly back into 2 helium nuclei. The only reason carbon gets made at all is that carbon-12 has a nuclear energy level, a specific quantum state, that sits just above the combined energy of a beryllium-8 nucleus and a helium nucleus. This near coincidence, this almost resonance, means that the probability of the 3rd helium nucleus arriving and fusing before the beryllium decays is vastly enhanced from virtually impossible to merely very unlikely, but likely enough to happen in the extreme conditions of a stellar core. The physicist Fred Hoyle predicted this nuclear resonance in 1953 before it was measured on the grounds that carbon exists in the universe, and therefore the physics must permit its creation When the resonance was subsequently confirmed experimentally, it was one of the most striking validations of reasoning from observed facts to underlying physics in the history of science. Carbon exists because the energy levels of carbon, 1, 2, happen to sit in just the right place for the triple alpha process to work. Move that energy level by a few percent in either direction, and carbon would not form in stellar interiors. There would be no organic chemistry. There would be no you. I find that worth sitting with. Not as an argument for design, but as a statement about contingency. The universe you live in, the universe in which you are made of carbon, is a universe in which the energy levels of carbon, 1, 2, happen to be exactly where they need to be. That is either a remarkable coincidence, an anthropic selection, or evidence of something we do not yet understand. All three options are interesting. After helium burning, the sequence continues. Carbon burning begins at about 500 million degrees and produces neon, sodium, and magnesium. Neon burning at about 1 billion degrees produces oxygen and magnesium. Oxygen burning at about 2 billion degrees produces silicon, phosphorus, and sulfur. Silicon burning at about 3 billion degrees produces a range of elements in the iron group: iron, nickel, cobalt, chromium, manganese. And then silicon burning stops. Not because the star runs out of silicon, though it does, but because iron represents a fundamental limit of stellar nucleosynthesis. Iron has the most tightly bound nucleus of any element. Fusing iron into heavier elements does not release energy. It consumes energy. A star that begins fusing iron is not generating power to hold itself up. It is draining energy from its reserves. And the result, when the iron core reaches a critical mass of about 1.4 solar masses, is catastrophic. The iron core collapses. Not slowly, not gradually. In less than a second, the core goes from a size comparable to the Earth to a sphere roughly 20 kilometers across. The density increases to a point where atomic nuclei are crushed together and individual protons and electrons merge to form neutrons. The core becomes, in a fraction of a second, a neutron star. And the outer layers of the star, which have been moving inward under gravity as the core collapsed, hit that incompressibly dense neutron star surface and bounce to do. The bounce generates a shock wave. That shock wave moves outward through the still collapsing outer layers of the star. The details of how that shock wave propagates, how it is energized by the torrential flood of neutrinos pouring out of the newborn neutron star, how it reaches the outer layers with enough energy to blow them off the star entirely. These are among the most complex and still not fully solved problems in computational astrophysics. What we know for certain is the outcome. The outer layers of the star, containing all the elements that stellar nucleosynthesis has built over the star's lifetime, are expelled into space at velocities of tens of thousands of kilometers per second. The star becomes a supernova. And here is where your personal atomic biography becomes even richer. Because not all the elements in your body were made during the steady stages of stellar burning. Some of them were made in the supernova itself. The supernova explosion creates conditions of temperature and neutron density that do not exist anywhere during the star's normal life. In particular, there is a process called the R process for rapid neutron capture that operates during the final moments of a supernova or during the collision of neutron stars. In the R process, nuclei are bombarded with neutrons so rapidly that they cannot decay before the next neutron arrives. This builds nuclei far heavier than iron, nuclei that are neutron-rich and unstable, which then decay back towards stability, producing a range of heavy elements: gold, platinum, uranium, thorium, iodine, selenium, barium, the heavy elements that cannot be made by any process in a normal stellar interior, were made in the most violent events the universe produces. The iodine in your thyroid gland was made in a supernova. The gold in any jewelry you are wearing was made in a neutron star collision or a supernova. The uranium in the Earth's interior, which contributes to the radioactive heating that drives plate tectonics and makes our planet geologically active, was made in one of the most violent events the universe has ever produced. You carry the products of cosmic violence in your body and in the world around you. Now I want to take you to the specific stars, because while the story of stellar nucleosynthesis is general, there are specific stars whose deaths contributed materially to the molecular cloud from which the sun and the solar system eventually formed. We can identify some of them, not all, but some. The solar system formed about 4.6 billion years ago from a collapsing molecular cloud in what was then a relatively unremarkable region of the Milky Way's disk. That cloud had been enriched over billions of years by the deaths of earlier stars, stars that lived their lives and exploded in the region before our sun formed, seeding the local interstellar medium with the heavy elements that eventually became the planets and the life on them. We know this not in the abstract, but in the specific, because the solar system's primordial material left a record in the oldest objects we can find. Meteorites, particularly a class called carbonaceous chondrites, contain tiny grains of material, smaller than the width of a human hair, that survive the formation of the solar system without being melted or chemically processed. These presolar grains are tiny time capsules from before the sun formed. They carry isotopic ratios that are dramatically different from the average solar system composition, ratios that identify them as coming from specific types of stellar environments. Some of these presolar grains are silicon carbide, formed in the outflows of carbon-rich asymptotic giant branch stars, stars in the late stages of evolution that shed enormous amounts of their outer layers in stellar winds. Others are graphite grains from the same sources. Still others are tiny diamonds formed in supernova shockwaves, carrying isotopic fingerprints that identify them as products of specific types of supernova nucleosynthesis. And there are presolar oxide grains, tiny bits of corundum and spinel that formed in the oxygen-rich outflows of red giant stars. These grains tell us that the material that built the solar system, including the material that eventually became you, came from many stellar generations. Dozens of stars, perhaps hundreds, contributed their nucleosynthetic products to the cloud that became our solar system. Each star had a different mass, a different lifetime, a different nucleosynthetic history. The carbon in you might have been made in a star 8 times the mass of our sun that lived for 30 million years before exploding. The nitrogen might have come from a different star entirely. The calcium in your bones might have been produced in a star that exploded 2 billion years before the Earth formed. But there are specific candidates that I find particularly striking. Stars that we can point to in the sky today and say, with real astronomical evidence, that star contributed to your existence. The first is a star called Zeta Puppis. Zeta Puppis is a hot blue star in the constellation Puppis, roughly 1,400 light years from Earth. And it is one of the most massive and luminous stars in our galactic neighborhood. It has roughly 17 times the mass of our sun and is burning so furiously that it will exhaust its nuclear fuel in only a few million more years. But Zeta Puppis is not remarkable because of its future. It is remarkable because of what it tells us about its past, the elemental composition of its surface. The nitrogen and carbon ratios visible in its spectrum show that it has already processed and dredged up material from its interior. It is already showing us the products of the CNO cycle, the carbon-nitrogen-oxygen fusion cycle that operates in the cores of massive stars on its surface. Zeta Puppis is a window into the kind of stellar processing that built the light elements in your body. A more direct connection comes from isotopic evidence in the early solar system. Researchers studying ancient meteorites have found evidence for short-lived radioactive isotopes that were present in the solar nebula at the time the sun formed. One of the most significant is aluminum-2,6, a radioactive isotope with a half-life of only 720,000 years. Aluminum-2,6 decays to magnesium-2,6, and the excess magnesium-2,6 found in certain meteorite minerals tells us that aluminum-2,6 was present in the early solar system in abundance. The only way to explain that abundance is that a massive star exploded relatively close to the forming solar system, within about 25 light years, within about 1 to 2 million years before or around the time the sun formed. The aluminum-2,6 from that explosion was incorporated into the solar nebula while it was still radioactive. That nearby supernova did more than contribute aluminum-2,6. The shock wave from the explosion may have actually triggered the collapse of the molecular cloud that formed the Sunday. We may owe our existence, the existence of the solar system itself, not just to the enrichment of heavy elements by previous stellar generations, but to the specific violent death of a specific star that happened to be nearby at the right moment. A star whose shock wave compressed our ancestral molecular cloud past the threshold of gravitational instability, initiating the collapse that became the sun, the earth, and everything on it. We do not know the name of that star because it exploded 4.6 billion years ago, before the earth existed. But we know it existed. We know it was massive. We know it was close. And we know that without it, the solar system might never have formed. There is another star I want to tell you about, one that is more visible and more personally resonant. That star is Betelgeuse. Betelgeuse is the red supergiant that forms the left shoulder of the constellation Orion, visible on any clear winter night in the northern hemisphere. It is enormous, so enormous that if it replaced our sun at the center of the solar system, its surface would extend beyond the orbit of Jupiter. It is roughly 20 times the mass of our sun, 700 times its diameter, and so luminous that it puts out 100,000 times more energy per second. It is a star in the late stages of its life, burning through its remaining nuclear fuel at a frantic rate, and it will explode as a supernova at some point in the next 100,000 years, possibly much sooner. When Betelgeuse explodes, it will be visible in daylight. It will cast shadows at night. It will be the most dramatic astronomical event any human being has ever witnessed, and it will shower the solar system with a wave of electromagnetic radiation and particles that, while not dangerous, at our distance of about 700 light years, will be measurable and real. More importantly, for purposes of this conversation, the explosion will send a wave of enriched material, the products of 20 solar masses worth of stellar nucleosynthesis, out into the interstellar medium of our galactic neighborhood. Betelgeuse will not enrich the material that becomes our sun's next generation of planets. We are not forming new planets, but the elements it expels will drift through the local interstellar medium for millions of years, eventually mixing into the molecular clouds from which future stars and planets form. The heavy elements in future life forms, billions of years from now, in some solar system not yet born, will include material from Betelgeuse. From a star we can see tonight, a star we have named, a star that has been visible to human beings for as long as human beings have looked at the sky, there is something extraordinary about that. You can go outside tonight, look at the shoulder of Orion, and see a star whose death will contribute to the atoms of life forms that do not yet exist. The stellar life cycle, the chain of nucleosynthesis and explosion and dispersal and condensation and life is not abstract history. It is happening right now, and you can watch it. Now, I want to bring this home because I think the nuclear biography of your atoms deserves a conclusion that matches its beginning. You are approximately 7 billion atoms. That is a 7 followed by 27 zeros. Of those atoms, roughly 60% by mass are oxygen, about 23% are carbon, about 10% are hydrogen. The remainder is nitrogen, phosphorus, calcium, potassium, sulfur, sodium, chlorine, and traces of dozens of other elements. Every atom of oxygen, carbon, nitrogen, phosphorus, calcium, and everything heavier was made inside a star. Your hydrogen came from the Big Bang. Everything else came from stellar nucleosynthesis, from the steady burning phases of stars that lived and died before the solar system existed, and from the violence of the supernovae that ended those lives. The iron in your hemoglobin, the molecule that carries oxygen in your blood, was almost certainly made in a type Ia supernova, a specific kind of stellar explosion that involves a white dwarf in a binary system accumulating material until it reaches a critical mass and detonates completely, leaving no remnant. Type Ia supernovae are the primary producers of iron in the universe. The iron in your blood arrived here from an explosion so total that nothing survived it. The star that made your iron is completely gone, not collapsed into a neutron star, not fading as a white dwarf, gone, completely converted to energy and dispersed elements, including the iron that ended up in your hemoglobin. The calcium in your bones was made in the oxygen and silicon burning stages of a massive star's core. The phosphorus in your DNA was made in similar stages, perhaps in the same star, perhaps in different ones. The nitrogen in the amino acids that make up your proteins was made in the CNO cycle, the fusion cycle operating in the hot cores of stars, more massive than about 1.3 solar masses. The oxygen that you breathe, that reacts in every cell of your body to release the energy that keeps you alive, was made in the helium-burning stages of massive stars. You are the current address of atoms that have been on an extraordinary journey. Some of them have been inside multiple stars, manufactured in one stellar generation, expelled in a supernova, incorporated into a later generation star or planet, processed through that star's evolution, expelled again, drifting through the interstellar medium for hundreds of millions of years, condensing into the solar nebula that formed our solar system, incorporated into the early Earth, cycling through geological processes for billions of years, eventually finding their way into the biological molecules of the life that emerged on this planet, passing through countless organisms over billions of years of evolution, and arriving finally here, in you. Now, the carbon atom at the tip of your finger has been part of a star. It has been part of the interstellar void. It has been part of the ocean. It has been part of some ancient bacterium, some early fish, some mammal that lived and died millions of years ago, some plant that grew in a forest that no longer exists. It has been exhaled and inhaled by organisms whose names we do not know and whose existence we can barely imagine, and now it is you. This is not poetic exaggeration. This is the nuclear and chemical history of matter as physics has been able to reconstruct it. The atoms are real, their histories are real, and the connections they imply are real. There is a question that this story raises, a question that I find genuinely difficult and genuinely important, and I want to sit with it rather than dismiss it. The question is what it means to be made of this material. Not chemically, not biologically, but philosophically, and in whatever sense goes beyond the merely physical. Because here is the thing that bothers me when I think about it carefully. The atoms that make up your brain, the atoms involved in every thought you have, every memory you form, every experience you undergo, those atoms have been part of stars. They have been forged in nuclear fires at temperatures of billions of degrees. They have been expelled in explosions that released more energy in seconds than the sun releases in its entire lifetime. They have drifted through the void between stars for hundreds of millions of years. They have been part of the Earth since before life existed on it. And now they are generating the experience of reading these words. They are creating the awareness of your own existence. they are producing somehow the subjective quality of being you. The same atoms that were in a stellar core 4 billion years ago are, right now, implementing consciousness. Whatever consciousness is, it is what these atoms are doing now, in this configuration, at this moment in the universe's history. I do not know what to make of that fully. I do not think anyone does. The hard problem of consciousness, the question of why physical processes produce subjective experience, is not solved by knowing that the physical processes are made of star stuff, but the knowing changes something. It changes the relationship between the me that is thinking and the universe that made the material doing the thinking. It makes the boundary between self and cosmos thinner than it usually feels. You are not separate from the universe, contemplating it from the outside. You are the universe in one of its local configurations, contemplating itself. The atoms that are you were in the universe before you were born and will be in the universe after you die, in different configurations, in different places, continuing their extraordinary journey through stellar interiors and interstellar voids and biological systems and geological processes and whatever comes next. The star that made you exploded so that you could exist. Not deliberately, not with knowledge of you, but necessarily, because without that explosion, the atoms would never have been here, the solar system would never have formed, and the remarkable chain of events that led to this moment would never have started. Go outside tonight, find Orion, look at Betelgeuse. That red point of light in the shoulder of the hunter is a star 20 times the mass of our sun, burning its remaining fuel faster than any human civilization has existed, approaching an explosion that will seed the galaxy with the elements of future life. The star that made your iron is already gone. The star that will contribute to life we cannot imagine is visible tonight with the naked eye. And the atoms in your body are part of this story, not as passive recipients of stellar generosity, but as the universe's way of continuing, complicating, and becoming aware of its own extraordinary history. That is what you are made of, not just stardust. The specific, traceable, nuclear history of matter from the Big Bang to this moment, and the history is not over. If this landed for you, if you find yourself looking at your hand differently now, or thinking about what it means that your atoms have been inside stars, I want to know. Tell me in the comments. These conversations are the reason I keep going deeper. And subscribe if you want more of this, the real physics of what you are and where you came from, because the story of matter is the story of everything.